So example, find the Z transform of f of k equal to k into 5 raised to k, where k is greater than or equal to 0. Solution. First of all, you just find the Z transform of 5 raised to k, where k is greater than or equal to 0. We know by standard Z transform of a raised to k when k is greater than or equal to 0 is equal to Z upon Z minus a, where mod of Z is greater than mod of a. And therefore, I am getting here Z transform of 5 raised to k equal to Z upon Z minus 5, where mod of Z is greater than 5. Now, by using the property of Z transform, which is that property multiplied by k. So, by property of Z transform of k into f of k equal to minus Z into d by Z of Z transform of f of k. The same thing I can write as, if we consider Z transform of f of k as f of Z. So same thing I can write minus Z into d by dz of f of Z. And therefore, by using of this property, I am getting Z transform of k into 5 raised to k equal to minus Z d by dz of Z transform of 5 raised to k. And Z transform of 5 raised to k we already have. It is nothing but Z upon Z minus 5. You differentiate with respect to Z. Note that their condition mod of Z is greater than 5. So what is the derivative with respect to Z? So minus Z as it is, and derivative u by v rule. As we know, since d by dx of u by v rule, so v into du by dx minus u into dv by dx upon v square. So by using this, I am getting Z minus 5 into derivative of Z is 1 minus Z constant, and derivative of Z minus 5 is 1. Whole divides Z minus 5 whole square. So simplify this. So I am getting Z transform of k into 5 raised to k equal to minus Z inside, it is a Z minus 5 minus Z whole divides Z minus 5 whole square. So this plus minus Z get cancelled, and I am getting Z transform of k into 5 raised to k equal to minus minus plus, it is a 5Z upon Z minus 5 whole square, which is your required Z transform. Let's consider new example. Find Z transform of the function f of k equal to k plus 1 into 2 raised to k, k is greater than or equal to 0. Again, by standard Z transform, we know Z transform of a raised to k, where k is greater than or equal to 0 equal to Z upon Z minus a, where mod of Z is greater than a, where mod of a you can consider, and that is why I am getting Z transform of 2 raised to k equal to Z upon Z minus 2, and condition is what? Mod of Z is greater than 2. Now I want k plus 1 into 2 raised to k. So since f of k equal to k plus 1 into 2 raised to k, I can write it is k into 2 raised to k plus 2 raised to k. So therefore, what is Z transform of f of k? It is Z transform of k into 2 raised to k plus 2 raised to k. The same thing I can write as Z transform of, by linearity property, it is a k into 2 raised to k plus Z transform of 2 raised to k, and by here k into f of k. So by property of Z transform, I can write Z transform of k into f of k is nothing but minus Z into d by dz of Z transform of f of k. And if we consider Z transform of f of k is f of Z, it is nothing but minus Z d by dz of f of z. So by using this property here, I am getting z transform of f of k equal to minus z d by dz of z transform of 2 raised to k plus. So for this I am getting this one, and second term as it is. So plus z transform of 2 raised to k. So if we denote, this is equation number 1. So from equation 1, I can write directly z transform of 2 raised to k here. So minus z d by dz of, so what is the z transform of 2 raised to k? It is a z upon z minus 2 plus z transform of 2 raised to k is z upon z minus 2. So I am getting z transform of f of k equal to minus z u by v rule again. So what is u by v rule? Of derivative, it is the d by dx of u by v is nothing but v constant derivative of u minus u constant derivative of v whole divides v square. So I am getting here, so minus z as it is d by dz of this one u by v rule. So I am getting here z minus 2 into derivative of z is 1 minus z constant derivative of this is 1 with respect to z whole divides z minus 2 whole square plus z upon z minus 2. So I am getting here, if we simplify this, so it is a minus z in bracket z minus 2 minus z whole divides z minus 2 whole square plus z upon z minus 2. And that is why I am getting z transform of f of k equal to, note that here minus z plus z get cancelled and remaining is minus 2 into minus z, it is a 2z upon z minus 2 whole square plus z upon z minus 2. What is the condition? Mod of z is greater than 2, which is your required z transform of the given f of k. One may simplify more if you want, otherwise this is your final answer. So how to simplify? You can take here LCM is z minus 2 whole square. So I am getting here 2z plus z into z minus 2. So that is equal to, if we simplify it, so I am getting 2z plus z square minus 2z upon z minus 2 whole square, and this get cancelled. So it is equal to z square upon z minus 2 whole square. It is your required answer after simplification, but need not there. Up to this it is sufficient. So now new example, find the z transform of f of k equal to k square where k is greater than or equal to 0. So solution. So normally such type of example here only k square student may confuse. So same thing I can write as k square into 1. If I have z transform of 1, I can find z transform of k square into 1. How? By using property of k raised to n into f of k. So how to find z transform of 1? As we know, z transform of a raised to k. What is k here? K is greater than or equal to 0. We know it is a z upon z minus a, where mod of z is greater than mod of a. The same thing can I write z transform of 1 raised to k? It is a z upon z minus 1, where mod of z is greater than 1. So because 1 raised to k is nothing but 1, and I am getting z transform of 1 is a z upon z minus 1, where mod of z is greater than 1. And now by using a property of z transform, so by property of z transform of k raised to n into f of k equal to minus z d by dz raised to n into z transform of f of k. If we consider this is f of z, means z transform of f of k is f of z. The same thing I can write like this, minus z into d by dz whole square of f of z. And that is why I am getting z transform of k square into 1 equal to minus z d by dz whole square into z transform of 1. So what is it? It is a minus z d by dz whole square into z transform of 1 is z upon z minus 1. So I am getting that is equal to minus z d by dz into minus z d by dz of z upon z minus 1. So carefully you solve. This is a minus z d by dz, and here I am getting this is a minus z and a d by dz of this one, means derivative with respect to z. Since d by dx of u by v rule, it is nothing but v into du by dx minus u into dv by dx upon v square, and that is why I am getting here minus z into z minus 1. So derivative of this z is 1 minus z into 1 whole divides z minus 1 whole square. So I am getting that is equal to minus z d by dz of, so simplify it, it is a minus z. So numerator z minus 1 minus z upon z minus 1 whole square. Carefully you simplify. Don't consider this minus z into this minus z. You simplify this part first and then you multiply this one. So I am getting that is equal to minus z d by dz. So this plus minus z get cancelled. So here minus 1 into minus z. So I am getting z upon z minus 1 whole square. Again you take a derivative with respect to z. So that is equal to, so this minus z as it is, u by v rule. So z minus 1 whole square, constant derivative of z is 1 minus z constant, and derivative of this one is nothing but 2 into z minus 1 whole divides z minus 1 whole square square. It means that z minus 1 raised to 4. So simplify this, you will get a final answer which is nothing but z transform of k square into 1, means it is just k square equal to minus z. So we can common out here z minus 1, and inside I am getting 1 z minus 1 and this common, so minus 2z whole divides z minus 1 raised to 4. So 1 z minus 1 get cancelled, so power will be 3 remaining. So I am getting z transform of k square equal to minus z into, so z minus 1 minus 2z. So I am getting here z minus 2z, it is nothing but minus z minus 1 whole divides z minus 1 cube. So that is equal to minus, take inside, so I am getting z into z plus 1 upon z minus 1 cube, which is your required z transform. So z transform of k square is nothing but z into z plus 1 whole divides z minus 1 cube, required z transform. So next example, find z transform of 2 raised to k by k where k is greater than or equal to 1. So solution for that. So first you find z transform of a raised to k where k is greater than or equal to 1, and after that use the property divide by k. As we know the properties of z transform of f of k by k is nothing but integration z to infinity z inverse into f of z dz, where f of z is nothing but z transform of this f of k. So using this property we can find it. So that is why. So solution here, note that here when k is greater than or equal to 0 or k is less than 0, we have standard result for a raised to k. But in this case k is greater than or equal to 1, and that is why use your definition. So what is the definition of z transform? So by definition of z transform of f of k equal to summation k varies from minus infinity to infinity f of k into z raised to minus k. So here you consider f of k equal to 2 raised to k and k is greater than or equal to 1, and therefore z transform of 2 raised to k equal to summation k varies from 1 to infinity. F of k is 2 raised to k into z raised to minus k. As we know, the standard summation formula is r raised to k when k is 1 to infinity and r raised to k when k equal to 0 to infinity. And in this case, k equal to 1 to infinity, and that is why I am getting z transform of 2 raised to k equal to. So this formula is applicable where r raised to k. So before to that, you write in the form of r raised to k where k equal to 1 to infinity. So here z raised to minus k I can write in denominator z raised to k, and that is why 2 by z raised to k. So here r equal to 2 by z. So I am getting z transform of 2 raised to k equal to r means 2 by z upon 1 minus r means 1 minus 2 by z, where mod of r means 2 by z is less than 1. So simplify it. So multiply numerator and denominator by z. So I am getting z transform of 2 raised to k equal to 2 upon z minus 2, where 2 is less than mod of z, means here mod of z is greater than 2. And now we want to find 2 raised to k by k. So by using property, so this is equation number 1, and by using property of z transform of f of k by k equal to integration z to infinity z inverse into z transform of f of k. If we consider z transform of f of k is f of z, same thing I can write integration from z to infinity z inverse into f of z dz, and that is why I am getting here z transform of 2 raised to k by k equal to integration from z to infinity z inverse into z transform of 2 raised to k into dz, where k is greater than or equal to 1. So by using equation 1, I am getting z transform of 2 raised to k by k equal to integration z to infinity z inverse, and the z transform of 2 raised to k is 2 upon z minus 2 dz. So here I am getting integration z to infinity 2 upon z into z minus 2. Note that here z inverse I can write 1 by z. That is why I am getting here 2 upon z into z minus 2 into dz. So by partial fraction or direct formula you can separate it. So how? So since 1 upon z minus a into z minus b equal to 1 upon z minus a minus 1 upon z minus b, and here outside it is a minus b, means 1 upon a minus b. If we compare this one, 1 upon z into z minus 2, so I am getting here z minus 0, z minus 2. So that is equal to 1 upon a is 0 minus 2 in bracket 1 upon z minus 0 minus 1 upon z minus 2. Note that this 2 for a while you take outside. So that is why I am getting here, if we consider z to infinity integration and this 2 into 1 upon z into z minus 2 dz. So I am getting here, so left hand side z transform of 2 raised to k by k, and that is equal to, so integration 0 to infinity here 2, and I am getting 1 upon minus 2 into 1 by z minus 1 upon z minus 2 into dz. You can simplify here, I am getting z minus 2 minus z, means minus 2 get cancelled, so same thing. So verification also there. So I am getting this 2 and this 2 get cancelled, and this minus sign you adjust inside, and that is why here I am getting the reverse. So therefore that is equal to integration z to infinity, this 2 get cancelled, and 1 upon z minus 2 minus 1 by z into dz. So by using standard integration I am getting it is nothing but a log of z minus 2 minus log z, lower limit z, upper limit infinity. Note that when we are going to substitute upper limit as a infinity or infinity as a limit for logarithm, so it should be in the form of numerator by denominator, then only you can put this one infinity. So I am getting here it is a log a minus log b formula or property of logarithm. I am getting log of z minus 2 by z, and here lower limit is z, upper limit is infinity, and I am getting here as z tends to infinity I am getting 0 minus log of z replaced by z means z minus 2 by z. So therefore I am getting it is a minus log of z minus 2 by z. So this minus you adjust here, it is an inverse, and that is why it will be reverse. So what we get here? So I am getting z transform of 2 raised to k by k equal to log of z upon z minus 2, which is your required z transform. Note that here what is the value of this mod z? Condition initially we declared this 2 is less than mod z. It means that mod of z is greater than 2. So which is your final answer. So next example, find the z transform of f of k equal to sin ak by k, where k is greater than or equal to 0. So again f of k by k property. But before to that we should know what is the z transform of sin of ak. So solution for that. So as we know by this table, z transform of sin alpha k, where k is greater than or equal to 0, is nothing but z into sin alpha upon z square minus 2z cos alpha plus 1, where mod of z is greater than 1. So by using this table, I can write directly the z transform of standard sin alpha k, means in this case z transform of sin ak, and that is nothing but z into sin a upon z square minus 2z cos a plus 1, means alpha equal to a here, where mod of z is greater than 1. Now using the property f of k by k, so by using property of z transform of f of k by k equal to integration z to infinity z inverse into z transform of f of k into dz. As we consider z transform of f of k is f of z, so I am getting integration z to infinity z inverse into f of z dz. So that is equal to z to infinity integration z inverse into z into cos alpha, and therefore I am getting z transform of sin ak upon k equal to integration z to infinity z inverse into z transform of sin ak dz. So if we denote, this is equation number 1. So by using equation 1, z transform of sin ak, you substitute there. So I am getting that is equal to integration z to infinity z inverse into z transform of sin ak is nothing but z into sin a upon z square minus 2z into cos a plus 1 into dz. Note that here integration with respect to z, that is why sin a is a constant, you can take directly outside. So I am getting sin a integration z to infinity, and this z inverse into z, it is nothing but 1 by z into z, it is equal to 1. So I am getting 1 upon z square minus 2z cos a plus 1 into dz. So integrate this with respect to z. So here your integration part should be perfect. You try to obtain in the form of x square plus minus a square, because here z square and 2z make a perfect square. So how? Let's see here. I can write that is equal to sine A, this as it is, integration z to infinity 1 upon. So here you just consider this one and try to find the third term. How? So here z square minus 2 into z into cos A. So square root of z square is z and square is present there. So it is nothing but cos square A. So adjust this one. So I am getting it is a z square minus 2z cos A plus cos square A. So I am taking here additional cos square A, and that is why you just consider minus cos square A and a plus 1 already there. So as it is into dz. So make it a perfect square. So I am getting here that is equal to sine A integration z to infinity 1 upon it is a z minus cos A whole square plus. So this I can write it is a 1 minus cos square A into dz, and that is why I am getting that is equal to sine A into integration z to infinity 1 upon z minus cos A whole square plus sine square A into dz. Note that here it is a constant term, but here I want a function. So that function I can convert into single variable, means like a t. So put z minus cos A equal to x. So I am getting here x square plus a square formula, means 1 upon this is. That is our aim. So differentiate. So dz equal to cos A is constant. So dz equal to dx. What about the limits? If we consider limits here from z to x, what I am getting? When z equal to z, so put here z equal to z, so I am getting z minus cos A, that is x. And when z equal to infinity, so if we put infinity, so I am getting x also infinity. So by using this, I am getting what is left hand side? It is a z transform of sine ak by k equal to sine A into integration. So lower limit is now z minus cos A, upper limit is infinity 1 upon it is a x square plus sine A whole square. And what about dz? It is a dx. So using standard formula, I am getting since integration 1 upon x square plus a square dx, that is equal to 1 by tan inverse x by. So that is equal to sine A, that is a constant, and here I am getting 1 by A. If we compare this A, it is a sine A. So 1 upon sine A into tan inverse x. What is x here? So x by A means sine A. Lower limit is z minus cos A and upper limit is infinity. So here these limits for x, so here sine A is outside, constant. So I can take here sine A by sine A, it cancel actually, and upper limit tan inverse infinity, it is a pi by 2 minus lower limit, that is a tan inverse x replaced by lower limit. So I am getting z minus cos A upon this sine A as it is. Now you know that since pi by 2 minus tan inverse theta equal to cot inverse theta, and therefore I am getting z transform of sine ak by k equal to sine A cancel. So I am getting directly it is a cot inverse whatever theta, it is nothing but z minus cos A upon sine A, which is your required z transform. Don't forget here condition mod of z is greater than 1. So you mention there the condition mod of z is greater than 1, which is your final answer.